We're going to get into system of equations and inequalities this chapter. So a system of equations is basically two or more equations that have the exact same variables. And in this case, for the most part, we're just going to deal with two variables. So the one major thing is if you have an equation, let's say something like this. If you had like 3x plus 2 equals 12. You can solve this, right, just by subtracting the 2 and then dividing by the 3. Okay, but if you notice, there's only one variable in this problem. So I can solve those. Well, anytime you have an equation with two variables, you need two equations in order to solve. Okay, so just understand that. That's going to be huge. Anytime you have two variables, you need at least two equations in order to solve. And what we're looking for is to solve a system that has two equations. What we really want to try to find is one point, one ordered pair, that makes each equation true. Okay, we want to find one ordered pair. So there might be lots of points that I could plug in for x and y into this first equation that make it true. Okay, there's going to be lots of them. Okay, because if I graph that, let's just say I just graphed it, every single point that's on that line would work. It would work if I plugged it in. If I plugged it in for x and plugged it in for y, I'd end up getting 10 equals 10 in the end. Okay, if I plugged in any point that's on that line. But I want to find one point that works for this top equation that also works for this bottom equation. And just think, if I were to graph those two lines, what do you think that point would be? So if I graphed this top line, let's say it was something like this, and then I graphed this bottom line, it was down at -7, had a slope of 2, and it went like something like this. Which point would work for both these equations, you think? Which point would it be? Yeah, it'd be their point of intersection right there, okay, because it's on both those lines, so it should work for both equations. So there's going to be lots of ways that we solve our systems. Today we're mainly looking at graphs and the tables of our graphs. Okay, and we'll use our calculator to help us out with this. And over the next few days, we'll also solve, with our paper and pencil, and we'll use the process of elimination, and we'll use substitution. And eventually, we're going to actually solve using a matrix. Okay, so lots of different ways we can solve these guys. But today, prominently, we're going to deal with graphs and tables. So let's take a look at one of these. Right here. So I got two graphs. I got this red guy right here, -2x plus 2, and I got this blue guy right here. And if you notice, or purple, whatever. And why was I able to graph these guys? Well, if you notice, both these ones are in slope-intercept form, right? Y equals mx plus b. So in this first guy, this has a slope of -2, right? -2 over 1, down 2, right 1. It has a y-intercept of 2, right? So up here, it's got a y-intercept of 2. Same thing down here, slope of 1/2 and a y-intercept of -3, as you can see on this graph right here. So what would the solution of this system be? Well, it would be their point of intersection, this guy right here. That would be the point 2, -2. So there is the solution to that system. And I could prove that it is the solution by plugging it into each of these equations. So I could plug in -2 for y and +2 for x, right? Because I got -2 for y and 2 for x, and solve. Well, -2 times 2 is -4, and -4 plus 2 is -2. So that checks out. -2 equals -2. That works. Same thing right here. I could plug in -2 for y, right? Because I got that right here. And I could plug in 2 for x and check to see if it works. Well, half of 2 is 1, and 1 minus 3 is -2, so that works as well, right? So I just plugged it in and simplified and made sure that both sides of the equal sign are the same. So -2 would be the solution to this system up here, okay? And I solved it by graphing. So if I wanted to do this on a calculator, the couple different ways I could do this is, well, what I have to do is plot it, right? I have to graph these two guys. So I'm going to type in -2x plus 2 and hit enter. And then I'm going to type in, every time I do a fraction, I put it in parentheses, or I could do 0.5, I guess, as well. X minus 3 And I'm going to go ahead and graph those. And remember, if they don't show up right away, the best zoom is zoom standard. So 6, which I already have right here. So there's both graphs. Okay, so what I could do is I could try to trace to this point. Remember, I can hit trace and jump on one of my lines, and I could just move over until I get to about that point. You know, it's not exact though, is it? Okay, so it's hard to tell, you know, what exactly it is there. Another way to look at it is so what was my point? 2, -2, and I got pretty close to 2 and pretty close to -2, but like I said, it's not exactly. I could also look at its table. So if I go to the table, so I hit second in this graph button to get my table. All right, so here's your x coordinates. And here's the first equation and the second equation. So what do I want to look for? Yeah, where they match up. So if you notice right here, these both have -2. So that would be the point 2, -2. And since it matches for both of them, that is that point of intersection. So I could also look on the table. And sometimes you might have to scroll through and look and kind of tell, you know, how is one increasing or decreasing. And when they get closer and closer, but that's another good option. So if there's decimals, this wouldn't be very good by looking at the table. But if we have integers, it works out kind of nice. Okay, to find it exactly, if I go back to my graph, we have these calculations right here. It says calc. I could hit second calc, and I could calculate the point of intersection. So if I go down and select that, or I hit 5, that'll select it right away. It says first curve. Well, first curve just means pick your first graph. So I'm on my first graph, right? -2x + 2. I hit enter. It should automatically jump to the second curve, the second graph. So I shouldn't have to do anything besides hit enter again. And then it tells me to make a guess. Well, you're supposed to guess where the point of intersection's at, but you can guess anywhere. So really, I could just hit enter 3 times in a row, and it's going to tell me that the point of intersection is 2, -2. Okay, so all your answers should be in ordered pair. So when I write this as my answer, I'm going to say 2, -2 as an ordered pair with parentheses around it. All right, so now it says verify the point 2, -2 is a solution to this system. Well, we just did that, correct? We just plugged in 2 for x and -2 for y, and it worked for the first one, and I plugged in 2 for x and -2 for y to the second one, and it worked, right, because -2 equals -2. So that's how you verify. So if you want to verify that a point works, you just plug in. Just be careful. Your instincts do this. If you don't think through it, sometimes you accidentally plug the 2 in for y here, and then -2 for x there. Well, this is your x, and this is your y. So that is not correct. So don't just plug the first one into the first spot. So make sure that you plug -2 in for y. You know, this is always your y. So it's got to go in for your y. And then 2 in for your x. So that's the thing to watch out for. Don't accidentally do the first one. And I know somebody's going to do it. So just be careful. Think through it. All right. So it says, what is the solution of the system graph below? Well, let's go ahead and let's use our calculator here to graph them. Well, hold up. Which of these could I graph on the calculator already? This one. I can graph that one. And why is that? Well, because it's in slope-intercept form. I need to get the y by itself in order to graph. So this second one, I'm going to have to get in slope-intercept form. So I'm going to do that down here. I'm going to rewrite this. Plus y equals 1. So I need to get the y by itself. Well, to do that, I have to move this -x to the other side. So I got to get rid of it. Well, the inverse of a -x is to add an x. Whatever I do to one side, I do to the other side of the equal sign. So that's gone. I'm left with positive y equals. Remember, I always put the x term first, and I can't add an x and a 1. They're not like terms. So just x plus 1. So yeah, so I'm going to rewrite this guy as y equals x plus 1. So now I got to graph these two. So I'm going to go in. So this first guy has a y-intercept of 4 and a slope of -1/2. This next one has a slope of 1, right? We don't see the 1 there, and a y-intercept of 1. So I'm going to go in. I'm going to clear both these guys. That's the first one. And I can type it in any order. I'll just type what it says. 4 minus (1/2) x, and down, and I got x plus 1. And graph. So there's my 4 minus (1/2) x, and there's my x plus 1. So I could hit trace and go over and look and try to make a good guess. You know, if I made a good guess, it looks like it's going to be about like 2, 3. So that's going to be my guess. I'm just going to write my guess down here. So I'm going to go 2, 3. I'm going to put a question mark there. Let's look at our table and see if we can confer with that. So second table. So 2, 3. Yes, that looks good. So that is my answer. Remember, the y's have to match up. So 2, 3 is correct. And quickly, if I wanted to solve for it, remember, I can go to my calculations, second calc, hit 5 for intersect, and just basically hit enter 3 times. First curve, second curve, guess. There it is, 2, 3. Got it. Awesome. Well, same thing. I got to get this second one in slope-intercept form, so I'd have to subtract this 0.5x to the other side. Subtract 0.5x to the other side. So I got to rewrite this guy as y equals negative 0.5x minus 21. So I'm replacing that. So when I graph those two, let's see this. Now it's not going to be nice and clean anymore. So let's go y equals again. So I got 38 plus 2x. I'll delete the rest of that stuff. And then I got my new equation, negative 0.5x minus 21. We'll graph. Uh-oh, why didn't it show up? Well, look at my first equation. It has a y-intercept of 38. So that's, you know, right now if I look at my window, my y's are only going from negative 10 to 10. So negative 10 to 10. So a y-intercept of 38 is like way up there. So I might have to pick a different zoom. Remember, if I want it to fit on there, I have this fancy one called zoom fit. So I'm going to try that. I'm going to see if I can fit both lines. Zoom fit. So there we go. There's that 38 plus 2x. Oh, man, it's still not showing the point of intersection. So we might have to mess with this a little bit. Well, how am I going to get way to the left there? Well, these are my x's, right? So my negative x's, my positive x's over here. So if I go to my window, right now, I'm only going to negative 10 in my x's. So this is 0, this is 10, this is negative 10. So it looks like I'm going to have to go at least like twice as far. So I might even go to like negative 50 or negative 100. So I might have to edit my window to be able to see that. So I'm going to switch my x min, right, my x-axis. I'm going to drop it back all the way to negative 50. So this is going to take, you know, some reasoning skills on your part to change your window. Okay, so there's my 38 plus 2x. There we go. Now we got a point of intersection. So remember, I can hit trace, and I can scroll over and take a look and make a guess. You know, it's something like negative 23. Oh, it's in between there. Negative 23.5 and maybe negative 9. That's a pretty good guess, I get. I'm going to go negative 23.5 and negative 9. There's my guess. So I'm going to put a question mark by it. If I go look at my table, second table. So if I started going down this way, I should notice my y1 are increasing, my y2 are decreasing. So are they getting closer together? Now they're getting further away. So that's not very good. So I wouldn't want to go that direction. Just kind of have to think through this. I might want to go this other direction. Now they're getting closer together, closer together. What if I want to jump really quickly? Like, this is taking too long. Well, you see how it says table set in the blue up here? I could hit second table set. And this tells me where to start my table. Well, let's say I wanted to start at negative 20. I wanted to see where when x is negative 20. And this tells me what I'm going to count by. Counting by ones right now. I still like that. So I'm going to count by one still. So now if I go back to my table, oh, not graph, second table. Now it's starting me at negative 20. Now they're getting closer. 0, negative 2, negative. Okay, so I can keep going. Oh, it's getting close. So it's somewhere in between negative 23 and negative 24, right? Because I got 8, negative 9.5, and then it jumps to negative 9, and that jumped all the way to so it's somewhere in between there. And if I want to find it exactly, remember, I can hit my second calc and point of intersection. First curve, second curve, guess. There's the exact point, negative 23.6 and negative 9.2. So negative 23.6 and negative 9.2. And in this case, if I looked at it, so we could make a guess, but using that calculation is the best way. So if I plugged in this for x and this for y into both equations, you know, that for x and that for y, it should work out. Okay? So I think we're finding out, doing the actual calculation of the point of intersection is the best way, right? Selecting all the first curve, second curve, and taking a guess, that tells us exactly. All right, what about this? I'm going to take a look at this guy. Well, I got to get this first guy into slope-intercept form, so I got to add the 2x over. Add the 2x. So I got y equals 2x plus 1, right? That's what that changed into. What do I notice? I notice that the slopes are the same here. So the slopes are the same. What do you think that's going to make our lines look like if the slopes are the same? Well, I already got these graphed. I'll tell you, if the slopes are the same, they're actually going to be parallel lines. Well, do parallel lines ever intersect? No, they never intersect. Well, aren't the solutions of our systems the points of intersection? So if these never intersect, how many solutions is this going to have? Or what would its solution be? Yeah, there'd be no solution here. Not one solution would work. You know, I could plug in this point into this equation, right? Because that's on this purple line, and it would work, right? If I plugged in 0, 1, if I plugged in 1 for y and 0 for x, it would work. 1 equals 1. But if I tried plugging it in up here, it would not work. Okay, that point would not work because it doesn't exist. It's not on the second line. Okay, so that's why there is no solution to this system. Like there's solutions to each individual equation, but none to the whole system because they do not intersect. All right, so that's important to know. So if the lines are parallel or they have the same slopes, there is no solution. Well, another case would be this. So I got my first one in slope-intercept form, so that's good. Let's get this second one in slope-intercept form. So I got to add that 2x over, and I'd have 2y equals 2x plus 4. Remember, I could put 4 plus 2x, but we like the x term first because, you know, the mx plus b. And then we got to divide by 2 to get rid of that y, get the y by itself. And these 2's cancel, so I'm just left with x. And remember, since I divided here, I also have to divide here. So 4 divided by 2 is 2. And what do I notice about these two guys now? I have y equals 2 plus x and y equals x plus 2. These are the same equations. They're the same. They're the exact same line. So what point would work on each of those? Well, if I were to graph those, we'd have a y-intercept of 2 and a slope of 1. It's like up 1, right 1, up 1, right 1, up 1, right 1. That would be each of those lines. If I graph this bottom one, that would be that line. If I graph the top one, it would be the exact same line. So how many solutions would there be? Well, this would be a solution, 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 right? Every single point that on those two lines. So there's infinitely many solutions in this case. Infinitely many solutions. Does every single solution work? No. Would this point work for the system? The point 0, 12? No, that does not work because it's not on those lines. So you can't say like all real numbers or all solutions. There's infinitely many possible because these lines go on forever, right? But not every single point works. So infinitely many is a good way to word that when they're the exact same line. So there they'd have to have the same slope and the same y-intercept. So lots of different cases. But using our calculator to help us solve all these systems right now.